Hi and welcome. We are going to talk about area and arc length in polar coordinates today. We've dealt with area and arc length before in other types of functions, but today we're going to be doing that with polar coordinates. So, area and polar coordinates. If f is continuous and non-negative on the interval from alpha to beta, then the area of the region bounded by the graph of r equals f of theta between the radial line, theta equals alpha, and theta equals beta, is given by area is 1/2 from a to b, alpha to beta, of f theta squared d theta, which is 1/2 from alpha to beta of r squared d theta. Okay, there it is. There's the definition. Let's actually do it now. We are asked to find the area inside the cardioid of 1 plus cosine theta. Okay, well, first thing I'm going to do is kind of give us a little bit of a drawing here. So 1 plus cosine theta is going to be like 1, 2, 1, 1. We're going to have something that looks kind of like this. You know how terrible I am at drawing these, so, you know, we suffer through. But anyway, there's our cardioid. We're going to find the area between that. So our area is going to be equal to 1/2 times the integral from. Now, where does this start graphing? Well, this actually starts graphing. Let's go to my calculator here. Do I have it in the correct mode? I don't. Let's put it in the correct mode. 1 plus cosine theta. So you can see it started at 2, kind of at 2, 0 there, and then we loop around here. But if I trace this at 0, when theta is 0, r is equal to 2, and when theta is 2 pi, oops, maybe I can't get all the way to 2 pi. Let's do 2 pi minus 1. See what that's 2 pi minus 1. Let's do 2 pi minus 0.001. Okay, you can see. There we go. We get very, very close there. And we're just going to loop around. So that's what we want to find the area of. So we're going from 0 to 2 pi of, well, now we've got to put our r in there. We've got our r. So 1 plus cosine theta, quantity squared, d theta. Okay? Now, we can kind of expand this out. So this is going to equal 1/2 from 0 to 2 pi of 1 plus 2 cosine theta plus cosine squared theta, d theta, which of course, once we integrate, or well, we can rewrite this again using our trig identities. We're going to have 1 plus 2 cosine theta plus, I can rewrite cosine squared of theta as 1 minus cosine 2 theta over 2 d theta. And once I integrate this, I'm going to get 1/2 times theta plus 2 sine theta plus theta over 2, because that would be that 1/2 there, right? Plus theta over 2 plus sine of 2 theta over 4. And I'm evaluating this from 0 to 2 pi. So if I do that, I'm going to get 1/2 times 2 pi plus 2 sine of 2 pi plus 2 pi over 2 plus sine of 4 pi over 4 minus, and I can tell you right now we've got 0 plus 0 plus 0 plus 0. So this becomes 0, this becomes 0, this becomes pi. 2 pi plus pi is 3 pi, right? So this is 1/2 times 3 pi, which equals 3 pi over 2. Okay? So what is 3 pi over 2? Well, that's the area. That's our area of this cardioid right there. Beautiful. Okay, let's do another example. We want to find the area of 1 petal of 4 sine of 3 theta. Well, 4 sine of 3 theta, if I graph that, I'll do that right now. So we've got 4 sine of 3 theta. Well, beautifully, I have 3 petals there, right? And we want to know when when one petal begins and ends. So to do that, we need to know when it's going to be equal to 0, right? So we can set 4 sine of 3 theta is equal to 0. Of course, we divide by 4, we get sine of 3 theta is equal to 0. Well, 3 theta is going to be equal to 0 when? It's going to be 3 theta is going to be equal to 0 at 0 and at pi, right? sine of 3 theta would be 0 at 0 and pi. Well, then we divide by 3 here, so we get theta is equal to 0, and theta is equal to pi over 3. So we know that in this graph, which looked something like this, if we start at 0, it's going to be 0, and at pi over 3 is going to give us one loop, one petal there. So that's how we can find our area. So our area is going to be equal to the integral from 0 to pi over 3 of 4 sine 3 theta quantity squared d theta. Okay? And I'm just going to put that in my calculator. So math 9, 0, pi divided by 3 of 4 sine 3 theta squared d theta. And I get, oh, you know what I didn't do? I didn't multiply by half. That's the problem. Times 1/2. So this is approximately 4.18879. Okay? So that's approximately the area of one petal there. Well, if we wanted to find the area of all the petals, what could we do? We could just multiply by 3, right? Okay. Let's do another example. Find the area inside one loop of r squared equals 9 cosine of 2 theta. Okay, well, first thing we have to do is rewrite r. R is going to be the square root of 9 cosine 2 theta. And so let's graph that and see what we get here. Get the second square root of 9 cosine 2 theta. If I graph that, looks like I'm going to have, oh, that's very interesting, kind of a bow or an infinity symbol there, right? That's beautiful. Well, now we need to know when this is going to be equal to 0, because we just want one loop, so we want from here to here, right? So I'm going to set this equal to 0. So if I square both sides, I get 9 cosine 2 theta equals 0. I divide by 9, I get cosine 2 theta is equal to 0. Well, when is cosine equal to 0? Well, when 2 theta is equal to pi over 2, and when 2 theta is equal to 3 pi over 2. So if I divide by 2, I'm going to get theta equals pi over 4, and theta equals 3 pi over 4. Now, what's another way that we could write 3 pi over 4? If you know that this is pi over 2, this is negative pi over 2, right? So not just 3 pi over 2, but if I wanted to rewrite that as negative pi over 2, this would also be equal to negative pi over 4, right? Okay, hopefully that makes sense. So now we can actually find our area. So the area is equal to 1/2. Don't be like me on the last problem. Remember the 1/2 this time. From the integral from, and you could go from, I'm going to draw a quick graph of what we've got here. You could go from like pi over 2 or pi over 4 to 3 pi over 4, but I don't think it's going to work quite as well, just because of the way this graph draws, right? Like, you know, you would get here, it just wouldn't work. So I think it's going to be best to go from negative pi over 4 to pi over 4. And maybe I'll try this in my calculator and see if they work out. So the square root of 9 cosine 2 theta squared d theta. So let me pause while I enter this in my calculator. Okay, I entered this in my calculator and I got 4.5, which of course is equal to 9/2. So just trust me on that. But when I entered it, instead with from pi to 4 to 3 pi over 4, and I hit enter, I actually get an error, right? Because when, I don't know if you noticed this, but when I did graph this, I've got kind of this gap here. Like there's this area that doesn't actually exist. So that's why you can't go from like one to the other, and you have to go from negative to positive. So again, if I enter this again, and I instead go from negative pi over 4 to pi over 4, and I almost went to that, I get that 4.5, and that's going to give me a clearer answer of what the area of that loop really, really is, okay? And that's kind of the tricky part of graphing polar coordinates. But, all right, let's do another example. Find the area of the inner loop of the graph of r equals 2 minus cosine 2 minus 4 cosine theta. Okay, so with 2 minus 4 cosine theta, if we graph that, we've got, did I do this right? One moment, please. 2 minus 4 cosine theta. Okay, I've got a cardioid here, but I want to find the area of that inner loop, right? So I'm going to draw that, and I do some tracing here. I'm at -2 is my inner loop, pi over 2, looks like I'm at rattles. Anyway, so I'm going to have something kind of like this. Oh, so bad at drawing them. But first thing that we're going to have to do is find out when these loops happen, right? So I'm going to set 2 minus 4 cosine theta equal to 0. So -4 cosine theta equals -2. Cosine theta equals a positive 1/2. So theta is going to be equal to pi over 3 and 5 pi over 3. Let's actually trace that and see what we get. So if I trace pi over 3, I'm here at my 0, and if I trace 5 pi over 3, I'm there at my 0 again. So I see, okay, that's actually when that loop begins and ends. So now I can find my area. My area is going to be equal to 1/2 from pi over 3 to 5 pi over 3 of 2 minus 4 cosine theta squared d theta. I'm kind of running into things here. And if I put this in my calculator, pause to do that. Okay, and I did this, wait a minute. Okay, and when I actually enter this, I get 35.525, so it's about 35.5250. Now, as I'm seeing that number, I'm realizing that that's pretty large, and I think what happened is that, so I graph at 0 here to pi over 3, and then I come around to 5 pi over 3 to here. So I didn't actually find that area. I found it from like pi over 3 to here. I found the larger loop. So I'm going to leave that content there just because I think, you know, it's a good example of kind of the area, the problem. But what I should have done is actually calculate the area from 1/2 and taking this whole times 2 from, you know, from 0 to pi over 3, because that would be from here to here. It would be this part there of this 2 minus 4 cosine theta squared d theta. And actually I've done that, and I got, this is about 2.174065, blah, blah, blah. Okay, so the most important thing about these polar coordinates and finding the area of them is to be careful when you're actually calculating them. I think that's really important. Okay, let's continue on here. We want to find the area of the region that lies inside the circle r equals, wait a minute, pause for a second. Okay, inside the circle r equals 3 sine theta, and outside the cardioid 1 plus sine theta. Okay, well if I graph that, I'm going to go 3 sine theta and 1 plus sine theta. And I can see, so there's my 3 sine theta, that's my circle. And then my 1 plus sine theta is right there. And look, I've got another circle happening, slowly but surely. Actually a cardioid there, it kind of butts in. You can't see very well in my calculator. But let me draw kind of a graph of this. So I've got my circle, 1, 2, 3, and then I've got a cardioid here that kind of goes like something like this, okay? And we want to find the area outside the circle and, or inside the circle and outside the cardioid. So what's that? That's this space right here. So naturally we're going to need to find where these intersect. So we're going to set 3 sine theta equal to 1 plus sine theta. Right? So if I solve here, I get 2 sine theta is equal to 1. So sine theta is equal to 1/2. Well, when is sine of theta equal to 1/2? When theta is equal to pi over 6 or 5 pi over 6. So now I can actually calculate this area. Well, my area is going to be equal to 1/2 from pi over 6 to 5 pi over 6 of. Now, I need to actually use, remember back when we were actually calculating area between two curves, I need to calculate the area between these two curves. So I need to take 3 sine theta squared, this area, minus this, minus 1 plus sine theta squared d theta. And I'm going to go do that in my calculator right now. You don't have to watch this part. Oh no, it's frozen. Oh, no. Okay, and I calculated this and I got 3.141592. Guess what? That's actually pi. This is equal to pi. Okay, so hopefully that all makes sense and is easy to follow on your lessons. I'm going to stop here and then start a new video to talk about arc length, which is even more fun if you can believe it. All right.